Our story begins billions of years ago, long before humans, dinosaurs, or even the simplest life forms existed. Picture a vast, swirling cloud of dust and gas, remnants of long-dead stars scattered across the cosmos. This nebula, as we call it, held the building blocks of our solar system, the raw materials for a grand cosmic creation. Gravity, the architect of the universe, drew these particles together, pulling them closer and closer over eons. As the cloud contracted, it began to spin faster and faster, like a spinning top gaining momentum. The center, where matter accumulated most densely, grew incredibly hot. Temperatures soared, igniting the core and giving birth to a star, our very own sun. This fiery inferno bathed the surrounding disk of dust and gas in light and heat, shaping the destiny of our young solar system. Within this swirling disk, tiny particles collided and stuck together, growing larger over time. These growing clumps of rock and ice, drawn together by gravity's relentless pull, became the seeds of planets. Through countless collisions and near misses, these planetary embryos sculpted themselves from the primordial chaos. One such collision, a particularly violent encounter, would have a profound impact on our planet's future. A Mars-sized object slammed into the young Earth, blasting molten rock and debris into space. This cataclysmic event, a cosmic dance of destruction and creation, gave birth to our moon, a celestial companion that would forever influence Earth's destiny. After the fiery chaos of its formation, Earth began to cool. The molten surface, a sea of liquid rock, slowly solidified, forming the first crust. Volcanoes erupted across the young planet, spewing gases from the Earth's interior into the newly forming atmosphere. This early atmosphere, a toxic mix of carbon dioxide, nitrogen and other gases, was a far cry from the air we breathe today. As Earth continued to cool, something remarkable happened. Water vapor, released from the planet's interior and delivered by icy comets bombarding the surface, began to condense in the atmosphere. Rain fell upon the cooling crust, relentless and torrential for millions of years. These downpours filled the first depressions on Earth's surface, creating vast, shallow oceans. These primordial oceans, teeming with dissolved minerals from the Earth's crust, became the cradle of life. They provided a stable environment, shielded from the harsh radiation of the young sun, where the building blocks of life could interact and assemble. It was here, in the warm, shallow waters of a young planet, that the story of life on Earth began. The origin of life remains one of the greatest mysteries in science. How did inanimate matter, the simple chemicals dissolved in Earth's early oceans, give rise to the complexity and diversity of life we see today? While we don't have all the answers, scientists believe that life emerged through a series of steps, each building upon the last. Imagine the early oceans, a warm, chemical-rich soup. Simple organic molecules, the building blocks of life, formed spontaneously from inorganic matter. These molecules, driven by chemical reactions and bathed in energy from the sun and geothermal vents, began to interact in complex ways. Over millions of years, these interactions gave rise to larger, more complex molecules, eventually forming the precursors to DNA and RNA, the genetic blueprints of life. These self-replicating molecules enclosed within simple membranes became the first cells. These single-celled organisms, primitive prokaryotes, were incredibly simple compared to the complex life forms that would evolve later. Yet, they possessed the remarkable ability to replicate themselves, passing on their genetic information to the next generation. This marked a pivotal moment in Earth's history. Life, in its simplest form, had emerged. From this humble beginning, from these single-celled pioneers, would arise the incredible diversity of life we see on Earth today. Section 4, the Great Oxidation Event, breathing life into a barren world. For billions of years, life on Earth was microscopic, confined to the oceans and fueled by simple metabolic processes. Then around 2.4 billion years ago, a dramatic event occurred that would transform our planet forever, the Great Oxidation Event. This event, driven by the evolution of photosynthesis, would change the course of life on Earth and pave the way for the evolution of more complex organisms. Cyanobacteria, a type of photosynthetic bacteria, evolved the ability to harness sunlight to split water molecules and produce energy. This process, known as photosynthesis, released a byproduct that would have profound consequences for life on Earth: oxygen. Oxygen, toxic to many early life forms, began to accumulate in the atmosphere, slowly at first, then, in a dramatic surge. This influx of oxygen had a profound impact on Earth's environment. It reacted with methane, a potent greenhouse gas causing global cooling and the first ice age. It also led to the formation of the ozone layer, which shielded Earth's surface from harmful ultraviolet radiation from the sun. The Great Oxidation Event was a defining moment in Earth's history. It transformed a barren, oxygen-poor world into a planet capable of supporting complex life. The stage was set for the next chapter in life's epic journey, the rise of eukaryotes and the evolution of multicellular organisms. Section 5. From simple cells to complex life, a billion years of innovation. The evolution of photosynthesis and the Great Oxidation Event marked a turning point in the history of life on Earth. The stage was set for a new era of biological innovation, an era that would see the emergence of more complex cells and, eventually, the rise of multicellular life. Eukaryotic cells, characterized by their membrane-bound organelles and more complex internal structure, evolved around 2 billion years ago. These cells, larger and more sophisticated than their prokaryotic counterparts, were capable of greater complexity and specialization. This paved the way for the evolution of more sophisticated organisms with specialized cells for different functions. The transition from single-celled organisms to multicellular life was a major evolutionary leap. It required cells to cooperate, communicate, and specialize, developing into tissues and organs with distinct functions. This transition, driven by natural selection and the challenges and opportunities presented by Earth's changing environment, led to the first multicellular organisms, simple algae and colonies of cells working together. The billion years following the Great Oxidation Event was a period of remarkable experimentation and diversification of life. From simple multicellular organisms to the first animals, life explored new forms, functions, and ecological niches. This period laid the foundation for the Cambrian Explosion, a burst of evolutionary innovation that would forever change the face of life on Earth. Section 6. The Cambrian Explosion, life's wild experiment in diversity. Around 540 million years ago, life on Earth experienced an unprecedented burst of evolutionary innovation known as the Cambrian Explosion. In a relatively short period, geologically speaking, a stunning array of new body plans, sensory organs, and ecological strategies emerged. The oceans, once dominated by simple, soft-bodied organisms, became teeming with a dazzling diversity of life. During the Cambrian Explosion, the first true animals with hard parts, such as shells and exoskeletons, evolved. This innovation provided protection from predators and new opportunities for movement and feeding. It also led to the evolution of more complex ecosystems, with intricate food webs and predator-prey relationships. The Cambrian Explosion was a period of remarkable experimentation and diversification. Some of the strange and wonderful creatures that evolved during this time, such as the trilobites with their segmented bodies and compound eyes, would become iconic fossils, providing a glimpse into this pivotal chapter in life's history. Others, like the bizarre Opabinia with its 5 eyes and grasping proboscis, would leave paleontologists scratching their heads for centuries. The Cambrian Explosion marked a turning point in the history of life on Earth. It established the basic body plans for most major animal groups alive today, and set the stage for the incredible diversity of life that would evolve in the millions of years to come. Section 7. A planet transformed, the enduring legacy of life on Earth. From its humble beginnings in Earth's primordial oceans, life has transformed our planet in profound and enduring ways. Over billions of years, life has shaped the atmosphere, sculpted the continents, and influenced the very chemistry of the oceans. It has weathered rocks, built mountains of coral, and created vast forests that stretch across continents. The evolution of photosynthesis, the Great Oxidation Event, and the Cambrian Explosion are just a few highlights in the epic journey of life on Earth. Each step in this journey, driven by natural selection and the ever-changing environment, has led to the remarkable diversity and complexity of life we see today. The story of life on Earth is far from over. It is an ongoing saga of adaptation, innovation, and change. As Earth's environment continues to evolve, driven by geological processes and increasingly human activity, life will continue to adapt and diversify, finding new ways to thrive in a changing world. From the smallest microbes to the largest whales, from the simplest bacteria to the complexity of the human brain, life on Earth is a testament to the power of evolution and the enduring legacy of 3.8 billion years of life's journey.